As we've been discussing reactions, we talked even at the very beginning of the chapter about how some reactions happen very, very quickly, such as fireworks or burning. Those are reactions that happen quickly, while others happen very, very slowly. Something decaying or something rusting. Those are very, very slow processes. And so what determines whether a reaction happens quickly or whether it happens slowly, and for that matter, whether a reaction happens at all? Well, in order for a reaction to happen, the molecules that are going to be reacting have to come in contact with each other. They have to collide. And so reactions, recall that your molecules are always moving. We said that in a solid, the molecules are just kind of vibrating. If they're in a liquid, the molecules are kind of sliding past each other. If they're in a gas, the molecules are kind of like hyperactive flies, and they're banging all over the place and flying everywhere. And so for a reaction to happen, those molecules have to collide with each other to start with. And they have to be lined up properly so that they actually will react, and the electrons will be able to be transferred, or they'll be able to be shared, and they have to collide with enough energy for the reaction to happen. So I've got three specific things that have to happen in order for a reaction to happen when the molecules collide with one another. So I want to try to give you an example of what this actually means. We adopted my youngest daughter. I have 6 children. We adopted my youngest daughter, and when she came home, she couldn't speak any English, and she had been here maybe a year or so. She was learning to speak English, but she still wasn't super good at English, and the kids were out in the yard playing baseball. And as they were playing, she had batted and actually managed to connect the bat with the ball, and she's running around the bases, and she's standing on third base. And her brother is getting ready to bat. Well, my daughter didn't quite understand all the rules of baseball. And what she decided to do, I mean, what we told her was, once he hits the ball, then you run. Well, she didn't understand the when he hits the ball part. She just thought that when he got up there, she was supposed to run. So what happens is that he gets up there, he gets the bat like this, she takes off running towards home plate, which is where he is, because she's on third base and she's running straight toward him. And the pitcher pitches the ball, he swings the ball, or he swings the bat, and cracks her right in the head. So they bring her in, and she's got their blood gushing everywhere, and it doesn't look good at all. She ended up being okay. She just needed stitches up here. I don't want you to leave you with a bad part of the story and think that she got killed or something. She didn't. She needed some stitches right above her eye, but she was good beyond that. But here's what had to happen. First of all, the ball and her head had to collide with each other in order to make her injured. Secondly, they had to be lined up properly. I mean, if her brother had swung, you know, a little bit differently, it might have hit her in the arm, or it might have hit her someplace else. But as it was, it hit her right here, and she got hit right above her eye. And so they had to be aligned properly for that to happen. And it had to hit with enough energy. So, I mean, if he would have just taken the bat and just kind of barely tapped her on the head with it, nothing would have happened. But because he swung the bat so hard and hit it with enough energy, that's when her head, you know, got busted open, and she had blood going everywhere and had to get stitches. So, in this case, the bat and her head had to collide. They had to be lined up in the right position for there to be an injury, and he had to hit her hard enough with the bat. So that's just, she now hates baseball. She refuses to play baseball, and she tells people you should never try to steal home because it just doesn't turn out well. Okay, so similarly for a reaction, your molecules have to hit one another, and they have to be lined up properly in order so that all of their electrons can either be shared, or they can be transferred, or whatever needs to happen to make that new kind of molecule. So the alignment has to be there, and they have to collide with enough energy to make the reaction happen. So once these three criteria are met, is it possible to make a reaction happen more quickly than it would otherwise? Well, actually it is, and there are about I guess about 5 different ways that I could actually make a reaction happen more quickly. The first way that I could do that is to increase the surface area of the reactants. So what do I mean by that? Well, if you have, I believe one of your little mini experiments earlier in the chapter was that you had to take baking soda and you reacted it with vinegar. And if your baking soda was all clumped up and you squash those clumps to break them up into a powder, then that is going to increase the surface area. So something like, I'm just going to put break up large chunks. Because what's the case there is that if you have a large ball of something, you have lots of little molecules inside of here that don't have any contact with the vinegar that's trying to get to them from out here. If I take all of this and I break them up into smaller pieces, then when the vinegar comes in and hits them, the reaction will happen faster because there's a lot more of the baking soda molecules that are in contact with the vinegar. Okay, so increasing surface area, breaking up large chunks is going to make a reaction happen faster. Similarly, if you stir something, stirring something is going to make the reaction happen more quickly. Well, why is that? Well, if you've got all of your solid stuff sitting at the bottom, like if you're going to react the baking soda and the vinegar, and you've got all your baking soda sitting down at the bottom, and then you pour the vinegar on top of it, if you want to make it happen faster, you're going to mix it up so that the vinegar has a chance to get to all of the baking soda, and it doesn't have to work its way down through a pile of baking soda in order to react. So stirring something then just gets the reactants in contact with each other and gives them more of a chance to collide with one another. Okay. Something else that you can do to increase the chances that a reaction will happen, or to make a reaction happen more quickly, is going to be to increase the temperature. Now, why does that help? Well, if you recall our discussions on kinetic energy, we said that when the temperature goes up, the molecules move faster. And so if I increase the temperature, that means I'm also going to increase their kinetic energy. And when they increase in kinetic energy, they're moving faster and they're moving with more force. I think one of the examples I used then was that, you know, if you are walking down the street and you just bump into somebody, you're likely not going to get hurt. But then if you've got 2 soccer players who are running towards each other on the soccer field and they bam into each other really hard, they have a lot of kinetic energy, and so the chances are going to be much greater that one of them will be hurt. So again, you increase the kinetic energy of the particles, and you are going to, first of all, increase the chances that they're going to collide, but also that they're going to collide with enough energy to make that reaction happen. Okay? Fourth way that you can try to increase the rate at which a reaction happens is going to be to increase the concentration. Now, what do I mean by that? Concentration means how many molecules there are, like in a certain amount of space. So if you are in a swimming pool, it's got chlorine in it. You have bleach that your mom maybe uses in the washing machine to make the whites a little bit whiter. That's got chlorine in it too. Would you want to swim in bleach? Absolutely not. There's a whole lot more chlorine. The chlorine is more concentrated in a bottle of bleach than it is in a swimming pool. So the bleach is concentrated, whereas the chlorine in the swimming pool is not. Another example of that is ammonia. There is ammonia in a lot of cleaning products, especially in like window cleaners is where you can most often smell it. So like if you're spraying window cleaner and you smell that smell, a lot of times it's ammonia. Well, farmers also put ammonia on their fields because, especially if they're going to be planting corn there, the corn really needs the nitrogen that the ammonia can put into the soil. But the ammonia there is very, very concentrated. And my husband used to farm, and so he knew that if he was spreading ammonia and the ammonia popped off of the tractor, he knew that if that was going to suddenly be released out into the air, he needed to get out of the tractor and run as fast as he could, as far away from there as he could, because inhaling that ammonia could kill him. So inhaling ammonia in a window cleaner certainly does not kill you. It may not smell real great, but it certainly doesn't kill you. But the ammonia that's in some of these anhydrous ammonia tanks that are on the back of tractors, if that gets out, that certainly could kill you just by inhaling it. And it all has to do with concentration. The ammonia that's in the ammonia tanks that the farmers are pulling is very concentrated. The ammonia that's in the window cleaner is not. Okay, so increasing the concentration means you have a whole lot more particles there. The more particles that are there, the more chances there are that the particles will collide with one another. And finally, we're just going to talk on this one really briefly. You can add a catalyst. And what a catalyst is it's something that makes the reaction happen faster, but it isn't actually changed in the reaction. And we're not going to talk about the mechanisms of how all that works, but the example that I can give you is if you were able to do the mini experiment where you put in, you had yeast and you poured hydrogen peroxide over the top. What that does is the yeast causes the oxygen to be released from the hydrogen peroxide, and it makes it bubble. And so what happens is that if you let the reaction go as long as it will go and all the hydrogen peroxide is decomposed, you could come back later and dump more hydrogen peroxide in it and it'll bubble again. And you could come back later and dump more hydrogen peroxide in it and it'll bubble again. And that's because the yeast never gets used up. So a catalyst is something that speeds up a reaction. It makes a reaction happen, but it doesn't get used up in the reaction itself, okay? So 5 ways to make a reaction happen more quickly. 4 most common ways: increase surface area, stir it up, increase the temperature, and increase the concentration. And then you can also use a catalyst. We use catalysts all the time in our bodies to catalyze reactions as well. So 5 ways that you can increase the rate of a reaction, and then that's about going to wrap this chapter up for us.